Okay, yes.
The floor is yours. Thanks.
Thank you. Good afternoon, and thanks to the organizers for having me. And so this is a method of source apportionation or a source appointment that I have been working on for several years. And it's really a hobby of mine. I've done 5 of these models during almost 20 years. So this is when someone finds the money to do a project, I do it. And I want to show you. This is fundamentally different from the most used methods by the EPA, which are available from their website. So, let's see. No, doesn't want to. So there's a brief overview. This was started because of wishes presented by the authorities of Reykjavik just after the millennium shift. So I'll talk a bit about that and the analytical problem, both analyzing doing chemical analysis and also of creating the samples. Then I have something I call source simulation, which is at the heart of this methodology. And then I have done some data mining, which is also does not fit in with this conventional methods. And I'm using near-infrared spectroscopy. I've been working within agriculture where this is very widely used, but not very widely used in environmental sciences. Then finally to the point with modeling results and concluding remarks. So this is really the only serious air pollution problem we have in Reykjavik. And most of it comes from, or a very relevant amount comes from studded tires. So this is a specific problem, not unique to us. We have it in the Nordic countries also, and in other areas, I'm sure. But it was of interest, it was a sort of pressure from the public. We should ban these studded tires because each autumn when we put them on, you can see the pollution. And the pollution is only on days when there is little wind, and often when there are several days with still weather, this builds up. The particulate matter doesn't leave the ground, so it's thrown up again repeatedly by the traffic. And other expected sources were soil, apart from asphalt, ground by the studded tires or the studs. And we expected that the asphalt and our local soils were rather similar in mineral constitution or in element composition, since we were using local gravel or materials for the asphalt. Therefore, from the start, I included the near-infrared to get some measure of the organic content. And the main part of this is that I choose some sources and I make dust from them and collect them in the same way as the actual samples. And there are 2 reasons for doing this. One is that we have decomposition and separation processes, which mean that I can not just sample soil or asphalt directly, because there are different sizes of particles in it, and we want the small ones. This is not probably not very big problem with the Icelandic soil. It's a volcanic ash soils, and it has a very fine particle distribution. In one of our projects, I also had volcanic ash, because we had an eruption going on just before. And actually, we keep that source for a couple of years after an eruption, even if it's many kilometers away. And if we take this infamous eruption at Eyjafjallajökull, the particulate matter was estimated to be around 85% of the whole. So that's a very finely divided material. Now, in every sort of study like this, we will have overlap in elemental content, and therefore we will need a multivariate technique. See there. Back here. So I had a slide with pollution results from Reykjavik, which I put in earlier today, but it seems to have, I don't have the correct version. But the point is that we have very little PM pollution, and then we get extreme peaks during the winter months, from November to April. And I had data with 1 hour averages, and it went to quite high values. But the solution used here, or tested to solve this problem, is to collect samples from suspected sources and flush them past the inlet of a standard sampler. We have taken both PM10 and PM2.5 and let the sampler choose the small, through the impactor, take out the small fraction, and we should get very similar samples to the actual samples. And then we can do this near reflectance measurements, which are non-destructive, so we get information on the organic content before, and then they are dissolved, these filters, rather destructively, and we measure as many elements as we can. And that's this data mining, which I will mention later, is that I actually go in. Now I have a ICP-MS, and I can go in and search for peaks. Just find is there a fraction of a peak in the scan which is accompanying usual measurements, and then I include these elements if I can find the standard for them. And I also have to choose. I get 900 wavelengths from the NIR measurement, approximately, and I choose out their wavelengths, which are giving proportional signals according to the weight of the collected samples. So not all areas of the NIR scan are getting Beer's law on the, if I have two samples, one is 1 milligram and the other is a 2, I should get a double signal for the larger sample, and I use that to select NIR wavelengths. And basically with this software, I throw in everything I have, and then I can pull them out afterwards if the model suggests it. So you can say that, as this is a hobby of mine, while I'm doing this modeling, I am a nerd, a social nerd, and totally uninterested in the pollution, just in where it comes from. So you cannot ask me about the situation of the pollution in Reykjavik. I don't care about that when I'm this nerd. So I also have to warn that this is going to be, the remaining of this talk is going to be extremely boring. But I will try to go fast to technical details. So There is something from the real world. Here on the left I have how I collect the soot from a diesel car. I don't even bother to take the petrol, since in previous models they have negligible contributions compared with the diesel. And we also, since I started this work, we have much more diesel cars than earlier. And so we use this rather standard sampler from Thermo, and the exhaust is going in here and the barrel is almost full. And this is to get out. When I try to put it straight in, I got it full of water. So this flowing cold water is actually distilling out the water from the, and there is about 10 centimeters here at the top where the air or the exhaust is going through. For other samples, I simply here, instead of the barrel, I put a 500 milliliter flask, and I have a gun with compressed air and put in a sample and flush it through this yellow hose. And this is, I have taped around, there's an opening on the other side, so that what comes up this hose goes through here, and the sampler will pull in 1 cubic meter per hour and take its portion out of this. I have this picture here because I like it. In the first project, I actually found an instrument for simulating the wear by studded tires. So this contraption, you put in a piece of asphalt, and it's a very noisy thing, and it hammers on this, and you get a simulated dust from the wear from studded tires. So I missed this instrument. Now I do this with a drill, but this is a sort of contraption from Donald Duck. But still, I could live without it. So there's a rather simple set of expected sources. We have 2 soil samples. I'm here describing the latest project that is finished, which involves 2.5 micron PM and was completed in 2019. I have asphalt, also 2 samples which are taken. There were different asphalt types on this road junction. The road junction is probably the most trafficated or second most trafficated in Reykjavík, so we are not trying to find the overall picture, we are trying to assess the bad days and the worst situation by collecting there. And there's a station collecting other parameters at the same place, so this can be compared. But that's not the point here. As I said, we don't care about the pollution, just where it comes from. There is this diesel soot brake lining I got from the ventilation systems of 2 brake repair shops, and rather different systems. So one is full of iron and the other is not. Salt, we salt the streets to remove the ice, and this is not, I have not tried to collect this through the sampler. I think this is rather homogeneous and I don't have to. This will crack rather easily on the road, so I think it will, I have just dissolved it and measured. And I also tested tires, and I got no contribution from the tires, as I was surprised. But then I found somewhere on the web, I didn't find in the hurrying now, I didn't find the reference that tires never make that small particles, that they will never become PM. So they are a bit bigger and will float by. Very standardized. This is a very usual sampler. This is a conventional, or almost, anyway, it's a microwave oven and a ICP-MS. Not the newest you get, and then we have a Fourier transfer NIR instrument. And this has a fiber optic and a semi-sphere to spread the light. And we have a light source in there, and instead of pouring hay powder on top of it, I just place the filter with an O-ring between. So it's very easy to scan the filters. The window is smaller than the filter. You measure reflectance, which is logarithm of the 1 divided by the intensity that is reflected. This is like absorbance linear in concentration, or in the same way as absorbance. And we pre-treat the spectra with averaging in the instrument software, and then later through smoothing in the chemometric software. Usually these samples are run for 24 hours, and that's sort of regulation interval, and I have extended this to 72 hours, again because we are not looking to characterize the pollution, but to get as few as possible samples with signals below detection limits. So we want to get big samples. As I say, if you have a bright, clear day with no dust, that's a bad day for this nerd. And such days are simply thrown out of the dataset at once. The ICP-MS, as I told, any measurement, I can take older measurements of the suspected sources, and I can go in with zooming, and where I have a straight background line, I can zoom in, and if I find some small hump in there, I choose that element and throw it into there. And this is hoping that I will get something that's different from one source to the other, and that will compensate for the being very few sources, and so I can have 2 soil samples, even if they don't represent all the soils in Reykjavik, they are significantly different from the asphalt samples or the other sources. So I measured some 51 elements, I think, and after discarding some, I had 35 in, and you can see these are general usual analytes, and here down we have some rather strange one, which I threw in from this data mining, lanthanides, and then these bottom lines of the periodic tables here. And there are reasons. If an element in a source has very many results below the detection limit or around the detection limit, then I don't use it. If there are only a few, I put in 0. The detection limiter, where you have by definition plus minus 100% error, so I can say I get minus and plus values around there, and I just put in zeros there. And there are some people do it differently, and I don't think this is a problem really, the exact method of choosing this. In other cases, I get that I have my sources have less, all the sources have less of some analyte than an actual sample. It means that I cannot make a linear combination of the sources to produce a result for a actual sample, and then I don't use that either. In an early study, I got, for example, a lot of cobalt, and I didn't know where it was coming from, and it was, none of the sources could explain it, but these studs on the tires, I later learned they are made from tungsten carbide, which is melted into cobalt. So, and they are extremely hard, but still that was enough to produce higher cobalt than in any of the samples for that study. So In the salt, one could think I could just use sodium, but I got better modeling results by taking a few of the others, and this is of course a very poor quality of sodium chloride. It's not white, this salt that they are throwing on the roads. It's a cheap commodity, and it helps to have these elements here. And these are the element set. Then I have, they come later, then I have to account for the mass, of course. So I am adjusting the signals per milligram per mass unit of collected material, both for the sources and actual samples. And these are the measures for throwing out results here. And then finally, we will have very different scales for different variables, and we have an arbitrary scale for the infrared. So we do normalization and centering of all the variables, meaning that the average value comes out as 0, and we have equally spread plus minus values, and this is very conventional for multivariate data handling. So here is the near infrared. This is a portion of the spectrum that for a long time was not used, since everything organic has a response there. And with computers and multivariate software, you can separate, and even if you don't separate, you can get unique profiles from near spectra, and this is very widely used in agricultural analysis, especially forages and feeds, also in food analysis. And in our case, we don't have to or want to know what we are measuring there. Just we get some organic characteristic for this and this source, and that will be additive. So we will get a contribution from the sources into all these near variables, and we use them as if they were measurement for something actual. And since we are only want to know the contributions, it's irrelevant to know if this is phenols or whatever it is of organic nature. And here are the wavelengths that I took out, and then for the volcanic ash, which I tried here, there were very few. I didn't use it for the salt. There shouldn't be anything organic, and I didn't get any. I was just creating noise. But some of them, especially the soot, the diesel soot, and also the brake lining, we got on asphalt and soil. We get quite a lot of the relevant information from the infrared. This is a widely used software. I use a spreadsheet for pre-treating data, and it's a partial least squares or PLS model, which is a very flexible modeling technique. It's based on principal components, and rather than just taking out principal components and using that in multiple regression, which has also been tried, then there is done some rotation, and you take principal components for the unknown samples and principal components for the calibration samples, and you rotate till they get as similar as possible. And that gives, we will have, if we had all relevant sources and no noise, we would get a very clean solution just by principal component regression, but this is accounting for the real world, so to say. An important part for PLS is that it's not very sensitive to co-varying variables, and if you have spectra, you will have a whole peak where all the points are in one peak are co-varying, and that throws in noise, adds up noise in many multivariate techniques, but not very much in PLS, so that's one of the strengths. Then I have results, PM 2.5, Reykjavik, and these are the contributions here, and apart from this one sample, the numbers here are the samples, and I threw out some of the small samples from the good days for normal people, and then I add up all the contributions, and this is percent of the sample weight. So this is rather good in my opinion. So this is on, I don't know why this one, possibly there was something wrong with the treatment of the sample, the weighing or something, but the others are quite good, and this is a much more specific technique than these positive matrix factorization, which is mostly used, which is relying on the computation to actually take out the solutions to these matrix problems are eigenvectors, and each eigenvector is taken to be a source. And it's very relying upon the exact or the uncertainty of the measurements, and if you have bad measurements, these variables get less weight, and it does not mean that they are not important variables. So that's and I think it would be totally impossible with this general EPA method to, I would take that the volcanic ash, which I did not hardly see in this year, and the asphalt and the soils, they will all model as mineral dust in this usually, or this is mostly used algorithm, PMF. Up here I have several things to work on. I can choose how many principal components, and I can throw out variables, and I can give variables added weight. And we can see, to test the model, that I also model the sources. So here are the two soil sources, and they model as very close to 100% soil, whereas the others were all less than 5%, or most of them much less. I forgot to throw these minuses out here, so this is sort of the error you get in very low values, but they are modeling, the sources are modeling as themselves in the model, and totally they also are very close here to when we add up for each source. I have here an older source and an older model, and this one was not very successful, so I have thrown it out in the latest version. But that was PM10, and now we are doing a PM10 in a different place up in Akureyri, which is in North Iceland, which I hope to finish now before the end of the year. So, considering that I'm using very few source materials and they may or may not be very characteristic, through this data mining, having so many variables, this is giving, at least it looks well. And I think one could, if we took a more complicated scenario than Reykjavik, if you took Belgrade, I think you could improve source appointment by doing this first. And you could take obvious variables and you could model them, and then you would get the rest. You could pull out these variables and put the rest into PMR, for example. So this is not necessarily only competition to the existing method. So, thank you.
Thank you for this very informative and very nice in-depth presentation. I don't see any questions in chat, and since we are running a bit late, I will...
No, I have to publish it now. So.
It is, he's made Reykjavik standard reference material.
Thanks. Since we're running a bit late...
There was no question.
Yes.